speaker. Shun.
Okay. First, I want to thank the organizer for this opportunity to speak here. And my talk will still talk about the soft theorem, but we'll focus on some practical ways. I will use the soft theorem to fix some explicit amplitude. Okay. And this work is done with Zhang and Honghua. So soft theorem relates different points amplitude, so which means it gives some constraint between them. So if I have some lower point amplitude, and I can use the soft theorem to relate it to a higher point one. So here constraint, I mean I want to constrain the coefficients. For example, the 4 point, I have this amplitude. There are some Mandelstam variables and the coefficients. And I want to find the coefficients between different points amplitude. And I can use single soft theorem to fix this amplitude. And I can also use the double soft theorem to do the same, to do this thing. But as Zhang said, that the single soft theorem can be derived from the symmetry principle, like word identity. So once I fix this soft theorem, this relationship still holds along the algebraic flow. But the double soft theorem, there are at least two kinds of double soft theorem. And one of them will have to introduce a 4-point vertex. So it will be quantum corrected along the algebraic flow. And I'll also talk about another interesting thing is that soft theorem and the locality can imply unitarity, which means that when we want to fix some amplitude, we write down some ansatz first. And our ansatz contains some local operator, contact terms, and some factorization channels. And locality means that in the factorization channels, I only allow the simple pole. And the unitarity means the residue of the pole is to be two sub-amplitude product. So I'm gonna relax this restriction a little bit and see whether softs can still give the unitary answer. So just quick review of the single soft theorem. Just reduce the n+1 point amplitude to an n amplitude by this tau soft parameter. And for the nonlinear sigma model and the dBi, they all have a different soft order. And for the dilatant, it has some non-vanishing soft, so it can reduce to some lower points here. And okay, so single soft is expand one of the external momenta, and double soft I have to expand two of the external momenta. But I have two ways to expand these two soft momenta. One is to assign them the different soft parameter, tau p and tau q, and I perform a bivariate Taylor expansion. And the other is to assign them the same tau parameter and just perform one variable Taylor expansion. But that actually gives different result. And you might think why. It's because that when you consider this diagram, when P and Q is approaching 0, and this inner propagator goes on Shun. So it has some singularity when you do the double soft expansion. So the way you choose to take it soft actually will give a different expansion result. So for type A is directly related to the two consecutive single soft. You just, first, I want to expand P and Q. First, keep Q still hard, and P takes soft. So I have the first one soft extension. Then I further take Q soft. So I have two consecutive single soft here. Then I could collect the terms to get a double soft factor here. So this is the type A single soft theorem. It's also called sequentially soft. And the other one is simultaneously solved, which just, as I say, take these two P and Q assign them the same tau and perform the expansion. And we actually found that these two expansions only differ from this diagram. So I can relate type A to type B by this 4-point vertices. So their relation can be written into another operator form, and the operator depends on your 4-point vertex form here. So I will give you if your 4-point vertex is SQ plus TQ, S squared plus T squared plus U squared, then this is the form of this operator here. And you might, if you notice that this, for 4-point S squared, is just dBi amplitude. So dBi amplitude is, there are many, well-known results for the dBi amplitude in their literature. So they are actually talking about simultaneous solve, of course, because for dBi, if you take type A, then you already get 0 after you take the first momentum solves. How can you get other things? So obviously, they are meaning type B. Then we just calculate this difference, and plus type A is 0, so we reproduce the dBi result in the type B. So this result can be also calculated by our means like CHY. So we just use this diagrammatic way to reproduce this result. So I just introduced you the single solve and the different type A and type B double solve. And we can also discuss this root correction here because the type B we introduced the 4-point vertex. So it might modify the original solve theorem. So for dBi, is 4-point vertex is S squared, but in 4-dimensional, you will introduce the new terms is S to the 4th power. And we will find that indeed the tau cube order double solve will be modified. So I will use single solve to fix the dilatant 6-point amplitude explicitly. And this is the input. It's the 4-point SQ, this is S squared amplitude, and the 5-point SQ amplitude. And this is my 6-point ansatz. It comes from 2 local operators and the factorization channels. So this 2 coefficient is the coefficient I want to fix. So, this S I just Mendelssohn variable, and Pn means I have to symmetrize all the external legs because they are bosons. Then I generate some numerics put into the Sij. Then I have to rescale one of the momenta by tau and do the series expansion to get the tau 0 and the tau 1 solve their equation. So these are just some numbers times these coefficients. Then I just solve them. Then you will find this is the result. I fixed the 6-point amplitude by the leading and the subleading solve theorem of dilatant. And I can further use this 6-point ansatz and feed in to fix the 7-point amplitude and so on. I'll just mention the solve and the locality can imply unitarity. So when I write on the 6-point ansatz, I write this factorization channel as 2 4-point amplitude. But if I can write other terms sitting on this simple pole, like this one is obviously not a product of 2 4-point vertices. But after I impose solve theorem, this term will be automatically ruled out. So this is what I mean that solve theorem and the locality can imply unitarity. So only simple pole and compatible with solve, and I get a factorization on my pole. And of course, I can also use the double solve to fix the amplitude. This one is a dBi amplitude. Then Again, I just generate some random numerics, and this I have to rescale 2 of the external leg. And here I'm using a type B DBI and DBI software, so I have to rescale them by the same tau. Then again, I just collect each terms, and then I get the linear relation between these coefficients, and I just solve them and to fix these 2 coefficients. So, okay, let me briefly conclude. So we can use soft theorem to fix amplitude. And the amplitude fixed by single solve of type A will survive the quantum correction because they are symmetry protect. But the type B, because I introduced the 4-point vertex, so this will be quantum corrected. And I also mentioned that solve and locality can imply unitarity. And this one actually is done by Nima and Tranka. They use the DBI 6-point and 8-point ansatz and demand them to vanish under single solve, and they can completely fix the DBI amplitude. And in our paper, we use the dilaton. I just tell you the 6-point one, and we can do the 7-point, and we finally get an 8-point answer. Okay, this is what I want to talk about. Thank you.
Questions? You have a question?
Well, I just had a comment. So you mentioned that what you call the type B double solve would be corrected as a loop now, which is true in the way you derive it. But I just want to say that we can write down what you call a version of your type B double solve a theorem that is valid to all the quantum. So well, of course we can talk about that offline.
I have a question. Okay, so the process you consider contains multi-scales or not? Yeah, if it's a single scale process, then it should not, the infrastructure should not depend on how you factorize source particles. So in our language, so I would say the type B is a factorization and type A is a refactorization of type B. So in principle, the infrastructure of the original diagram should not be changed. So when you do so, okay, you show a formula, right? You relate it to the type A and type B factorization here formula. So yeah, okay, this one. So you see, the right hand side, the last term is called the matching between these two. So this one should be infrared finite. If your process is a single scale process. If we consider the multi-scale process, then the story will be different.
You say multi-solve?
No. With this process, for example, there's several half scale. So there's several half scale. Right? If it is a single half scale, then the last term should be infrared finite. Because the infrastructure of the original diagram is fixed. It should not depend on how you factorize the source particles. Okay. Okay.
Also, I don't understand the statement about locality plus soft theorem implying unitarity. Unitarity is a highly statement. You can write down effective theory with satisfying some soft theorem or low energy theorem. The theory doesn't have to be unitarity.
Okay. Here I allow simple this what I mean locality. Then I can write down the numerators. And the numerators can be, here I consider 6 points. So the numerator can be 2 4-point amplitude, right? So this is just S squared plus T squared plus U squared 4-point amplitude. This one is what we mean unitary. But of course I can put other terms on this numerator, like this one. It's to satisfy the same power continuous of order S4, but this one is obviously not the product of 2 4-point amplitude, right? But after you put this ansatz and do the soft theorem, you'll find out this coefficient will be just automatically killed, just set to be 0. So this term, non-unitary term, cannot survive solve. cannot be compatible with soft theorem.
Maybe what you mean is a subset of the theory which is sensitive.
Let me make a comment. So I think what he's trying to say, or what Nima is trying to say in the paper he quoted is, if you have Yang-Mills, okay, gauge symmetry plus locality implies unitarity. Okay, and gauge symmetry is a symmetry, so it's not that surprising that it tells you about the UV behavior. So it's the same thing there when you move to a sigma model or ghost model. The soft theorem is dictated by the symmetry of the non-image sigma model. So maybe it's better to phrase it as that the symmetry of the sigma model plus locality implies
It's only the amplitude which is sensitive to the sigma model here. If you have another amplitude which I don't see this, and that part of the model may not be, it will not be constrained by this argument, right?
Which model?
I mean, I have another, I have a UV theory.
Right.
It means some part of the theory are constrained by this soft theorem, but then I can have, for example, a gravity sector. Well, gravity is not local, but I have, let's say I have another, write down a random one.
Well, okay.
Yeah.
In the gravity, it's the same thing. They did the same exercise. If you assume gauge varies plus,
I'm talking about gauge variance, I'm talking about this.
but it's the same thing. Soft theorem, you should really think of the soft theorem as the same status as gauge symmetry.
Let's say I call it R square gravity. R square is not in the theory, so I still have some soft theorem there.
But when you add R squared, that will modify your soft behavior.
Yeah.
Yeah, I think we should stop here because the organizer on the course the stop. Okay, so let's thank the speaker again. And according to the program, we should have 10-minute break. So let's come back at 11.